So we're going to talk about inverse functions, and just sort of tell you in general how inverse function works, and then we're going to look at some specific examples of inverse functions, okay, depending on how far we get into notes today. Right. So if you have a function, so if you're just given a function, so here in the notes it just says, suppose you're given a function f, then you can sometimes, but not always, you can define a new function based on f, which is called f inverse. Notice that the way we denote f inverse in function notation is we use this superscript of -1, okay? But don't confuse that superscript with being an exponent. That's not an exponent. That's just a notational device, okay? So that's just think of that as a superscript in this context and not an exponent. And again, it's just a naming convention. It's just a way that we conveniently can make up a name for this so-called inverse function. And here's the way the inverse function works, okay? So you've probably seen this before. With an inverse function, what you're going to do is interchange the inputs and the outputs for the original function. So in the original function, right, you may have an input x, and the matching output could be some value y, correct? Okay? All right, so what we do to define the inverse is we interchange the input and the output. So for the inverse function, if the input is y, the matching output will be x, okay? So we just flip the inputs and the outputs, all right? And that new function that you create this way, if it is indeed a function, but it may not have to be a function, okay? That new function that you're creating that way is called the inverse of the original function. And again, we use that superscript -1 just as a way to name that inverse function, okay? Functions do not have to have inverse functions, okay? So for some functions, you won't have an inverse function. But if a function does have an inverse function, it's called a one-to-one function. We'll get a feel for why that's where that name comes about here in just a second, okay? So if a function has an inverse, it's called a one-to-one function. So another thing you could say is the function has an inverse, or the function is invertible, or the function is one-to-one. All those phrases are interchangeable, okay? And if a function does have an inverse, it only has one inverse. So inverses are unique, okay? So a function cannot have more than one inverse function, all right? Okay. All right. So here is the actual test you can use. Here is the actual formal logical test you can use to determine if a function has an inverse function or not, okay? So if a function is one-to-one, that means it has an inverse. It has to meet this criteria, okay? This criteria is a little bit, when you read it symbolically, it's a little bit confusing to understand, but when you see it explained in words, it makes much more sense. Okay, so a function is one-to-one if this is the case, all right? If you pick two inputs that are not the same, okay, if you pick two inputs that are not the same, if their matching outputs are not the same, then then you know the function is one-to-one. That means the function has an inverse, okay? All right, so let me repeat that in words, because again, it's much easier to understand in words. A function is going to have an inverse. It's going to be one-to-one if, when you pick two different inputs for the function, two inputs that don't equal to each other, right, okay? If the matching outputs also do not equal each other, then you know you have an inverse function, okay? So if it's ever the case that you pick two inputs that are different, but the matching outputs turn out to be the same, then you know you don't have an inverse function, okay? You do not have an inverse function, all right? But if in every case when you pick two inputs that are different, you get two different matching outputs, then you know you have an inverse function. All right. Okay. All right. Let's apply that definition in one example. Okay. So I'm going to take this very simple function here, 3x plus 4, and I want to use this definition to show that it does have an inverse function. Okay, so I'm going to use this definition to show that it does have an inverse function. Okay, and then once we determine that it has an inverse function, then we're going to figure out what the formula for the inverse function looks like. Okay, I'm not going to worry about the graph yet. Okay, but we want to figure out what the formula for the inverse function is. Okay, all right. This is a very simple function, right? What kind of function is this? Yeah, it's linear, right? So when you graph this, you're going to get a straight line. That's about the simplest type of function you can deal with, right? Okay. All right. So I claim that this function does have an inverse. Okay. All right. So here's how I'm going to demonstrate this. Okay. Let's suppose that it didn't. Let's suppose that it didn't have an inverse, okay? So suppose it didn't have an inverse, then what would be the case? If it doesn't have an inverse, what's going to be the case?
The outputs would be the same for different inputs.
Yeah, the outputs would be the same for two different inputs, right? Okay? Because if it does have an inverse, right? If it does have an inverse, then when you pick two different inputs, you get two different outputs, correct? Okay? So if it doesn't have an inverse, that means that there must be a couple of inputs laying around, right? Okay? Where those two inputs give you the same matching output, right? Okay? All right. So let's write this down. So I'm going to pick a couple of inputs here, all right? I'm going to pick a couple of inputs here, x1 and x2. And let's suppose that f of x1 is equal to f of x2, all right? So suppose we pick these two inputs and they end up having the same matching output, right? When you plug x1 into the function, you get the same thing as you plug x2 into the function, all right? So if this is going to be a one-to-one function, what must be true for x1 and x2? No, because if they're not equal, right, okay, right, if x1 and x2 are not equal, then something bad has happened, right? Look, if x1 does not equal to x2, right, okay, then what do you know, Aaron? Well, we already said they're the same, right? Okay, so if x1 and x2 are different and these two are the same, then what do you know about the function f? Does it have an inverse? No, it doesn't, right? Okay, so then f won't have an inverse, right? So what do we want to show then? We don't want this to be the case, right? So what do we want to show? We want to show these two things are really equal, correct? Okay. Because if they're not, if it can be the case that they're not equal, then we don't have an inverse, right? But I want the function to, I wanted to show that the function does have an inverse, so I want to show that these two things must be the same, okay? So if x1 is equal, if f of x1 is equal to f of x2, I want to show here that x1 is equal to x2 as well. In other words, I cannot pick two different inputs with different matching outputs. That's not possible, okay? So I can't pick two different things here that would give me the same matching output, okay? All right, so let's see. Let's look at this equation then. F of x1 and f of x2. What's my formula for f of x? It's 3x plus 4. So what's f of x1 look like then?
3x1 plus 4?
Not 1, but what? plus 4, isn't it? Right? Okay. See, if you plug x1 into that formula, I covered up the formula, you get 3x1 plus 4, right? Okay. And then what's f of x2? Yeah, that's 3x2 plus 4, right? But remember, we were saying we picked x1 and x2 so that these two things are equal, right? So these two things must be equal as well, okay? All right, now, look, let's reduce this equation. Let's simplify this equation a little bit. We have 3x1 plus 4 equal 3x2 plus 4. That means you have the same 4 on both sides of the equation. So what can you do with that? You can cancel it, right? Okay, so we can cancel the 4's, and I get 3x1 is equal to 3x2. And now what? Now I have a multiple of 3 on both sides of the equation. So what can I do with that? You can divide that out, right? So we can divide that out. And what does that leave me with here? Yeah, I end up with just x1 is equal to x2, right? Okay, isn't that what we wanted? Right? Okay. If f of x1 is equal to f of x2, we wanted to show that x1 must be equal to x2, right? Well, there's f of x1, there's f of x1, there's f of x2, and what happened? X1 ended up equaling to x2. So there I did it, okay? I think I showed now that that function is one-to-one. See, if you have two outputs that are the same, right, then you know the matching outputs have to be the same as well. It's not possible to have matching outputs the same with two different matching inputs, okay? That won't happen, all right? So there we get it. All right, so 3x plus 4 does have an inverse. So it makes sense to write down. Here f inverse of x. I know that this function does have an inverse. So this notation makes perfect sense. Now the question I'm interested though is what is the formula for that inverse? What is the formula for that inverse? So, this is a function, right? So we should be able, we think, to write down its formula. So what will be its formula? See, what's the formula for f? You can't see it on the screen here, but what's the formula for f? 3x plus 4, right? So I'd like to see if I can figure out what's the formula for f inverse. Is it 2x minus 7 or 8x plus 1, or what will it be, right? Okay. Or maybe it's something weird like natural log of x. Okay, that doesn't seem likely, right? But maybe that's possible. All right, that actually is easier than proving that f has an inverse, okay? All right, that actually turns out to be conceptually kind of easy to figure out what the formula for the inverse is. All right, let me write down the formula for f using, instead of f of x, let's use the variable y for the output, okay? So let me write down that linear equation, y equal 3x plus 4. Remember, what does the function inverse do? Remember what I said, how you define a function inverse? What does it do? Yeah, remember our function inverse works that if the input to the function gives you y, then when you take this output and plug it into the inverse, you get the original input, right? Okay. So what an inverse does is it flips the inputs and the outputs of the original function. All right, flips the inputs and the outputs for the original function. Well, let's just do that, okay? What's my output variable for this function? What am I using for the output here? No, output. Y, right? What am I using for input? X, right, okay? So I'm just going to flip those. I'm just going to flip them. So I'm going to write x is equal to 3y plus 4, okay? And now let's just solve this equation for y, okay? So let's see, how do I solve this for y? That's pretty easy. Subtract 4 from both sides, right? And now divide by 3. And there it is. I claim that's my formula for my inverse function. So x minus 4 over 3, that is the formula for the inverse function. What kind of function is that? That's linear also, okay? So if f of x was 3x plus 4, then I claim it does have an inverse. We proved to ourselves that it does have an inverse, all right? And there is the formula for the inverse. It's x minus 4 over 3, okay? Not that unusual looking, right? Okay. Also a linear function, right? X minus 4 over 3 is also a linear function. We can make a graph of those two functions, and maybe we will in just a second, okay? Because their graphs also have a relationship as well, okay? That's easy, that has a geometric meaning to it, okay? That's definitely a function, right? So there's another way to sort of convince yourself that a function has an inverse. Just try to figure out what the formula for the inverse is. And if you can find the formula for the inverse, then that means the function has an inverse, okay? So this is definitely a linear function, right? This is also a linear function. This is a straight line, which is also a function. So this function f of x definitely does have an inverse. There it is, x minus 4 over 3. All right, now look, what I claim is this function does not have an inverse, okay? So x squared minus 2x, x cubed, I mean, minus 2x squared minus 3x, I claim that doesn't have an inverse, all right? Okay. So how am I going to convince myself that that does not have an inverse? So what does it take to not have an inverse? That means what? Not multiple y values, but the same y value with what? With multiple x values, right, okay? So you could have different inputs. You could choose different values for x here and get the same output. That's what prevents you from having an inverse, okay? If you pick the same, different x's and get the same y, then that means you will not have an inverse function, okay? So that's what I'm looking for to convince myself that this doesn't have an inverse. I want to see different x's that have the same output, okay? Can y'all, now, you may be able to guess at this and figure a couple of them out. Did anybody figure something out here? You see different inputs with the same output? Just try a couple of them and see what happens there. Okay, let's pick some inputs here and find the matching output, and let's see if we can just disprove that it has an inverse, or prove that it doesn't have an inverse just by trial and error. I'll pick an easy one. If you let x be 0, what's y? Also 0, okay? So if I can figure another x value that gives me an output of 0, then I know this doesn't have an inverse, right? So what's an x value that gives you an output of 0? What's that called? An x value that gives you a y value of 0. What's that called? That's got a name. What? X-intercept, right. So if I can find another x-intercept, that's where it's going to cross the x-axis. The graph's going to cross the x-axis. So if I can find another x-intercept, I'll know that this doesn't have an inverse, okay? Can you see another x-intercept here? You can try one here. What about, let's try 2. I'm just making that up, okay? So does 2 work? If you plug 2 in here, you get what, 8? Darn it, minus 8. Is that minus 6? Phooey. Okay, so 2 didn't work, right? Does 1 work? 1 minus 2 minus 3. No, that's something like minus 4, right? So that's no good either. What? Larry's going to try negative 1. Okay, I'm down with that, but you have to do the arithmetic for me, Larry. All right, okay.
X cubed, that would be
Negative 1.
minus, so negative 1 squared is positive, so negative 1 minus negative 2.
Negative 1 minus 2 is negative 3.
So 3 times negative 1 is a positive. It's a negative, but the double negative is a positive.
Ah, that gives you a 0, right? Yay! Okay, so Larry stumbled across one there, right? Okay. There are at least two x-intercepts, all right? One of them is 0, and there's another x-intercept. So there are two different, if we did the arithmetic right, so there are two different inputs that give you the same matching output. So it is not invertible, okay? It is not a one-to-one function, right? Okay. That function, x cubed minus 2x squared minus 3x, does not have an inverse. So it is not correct to write ever f inverse here, okay, right? Because there is no such thing, all right? This function does not have an inverse. Not all functions have inverses, okay? That's just the way it is, all right? Not all functions will have inverses. Let's actually look at a graph of x cubed minus 2x squared minus 3x, because that might help you figure out that it doesn't have an inverse without doing trial and error, okay? So let's actually look at the graph here of that function. So I'm going to go back to Desmos, and I have a screen here to help me with making graphs. And let me see if I can find it. It's just called Basic Function Graphing, all right? So in this screen, all you have to do is enter in a formula, and it'll make a graph for you, all right? So what was our formula? X cubed what? Minus 2x squared? Yep. Minus 2x squared, and then what? Minus 3x. Ah, there we go. Okay, so it made a nice graph, right? That's a nice graph of a cubic polynomial. X cubed minus 2x squared minus 3x is a cubic polynomial, so you know it's going to have some wiggles in it, right? Okay. In fact, it's going to have two turning points, okay, which you can find from using the first derivative, right? It has an inflection point maybe about right here, which you can find from using the second derivative, okay, right? And it's got three x-intercepts, which Larry already told us minus 1 is 1, right? There's the one at 0, and it had another one over here at 3, okay? So it actually has three inputs that give you the same output, right? Okay, so definitely not invertible. Now, how can you see from the graph that it's not invertible? Yeah, because you can see, and the x-intercept is just one example of this, right? You can see there are going to be lots of different x values that give you the same output, right? For instance, if you chose an output of being minus 2, correct, right? Then there's 1, 2, 3 x values that give you an output of minus 2, right? Okay. Or what about down here at minus 6? There's 1, 2, 3 x values that are going to give you an output of minus 6, right? So this is way not invertible, right? Okay, way not one-to-one, because there are lots of instances where they're the same input that give you the same matching output. What geometric feature in the graph suggests that? Well, that's the famous horizontal line test, okay? So if you've got a graph of a curve, right, okay, graph of a function, and you can draw a horizontal line that crosses the curve in more than one place, then you do not have a one-to-one function. It's not invertible, right? Okay. So the x-axis is an example of a horizontal line that crosses this curve in more than one place, right? Okay. That's why you have three x-intercepts. So not a horizontal line, right? Okay. Y equal minus 2 crosses it in 3 places. Y equal minus 6 crosses it in 3 places. So definitely not invertible. Doesn't have to cross it in 3 places. Just 2 would be enough, okay? So you can see from the graph that pretty quickly that this doesn't have an inverse, okay? Without having to write down specific values, you can see from the graph that it doesn't have an inverse. Well, kind of when they don't have inverses, that's not really fun for us, right? We'd rather them have inverses. This property is sometimes useful to us. This is called the inverse function property. If you want to test to see if two functions are inverses of one another without going through the process of determining, you know, what the inverse formula for one of them is and checking to see if it's the same as the other one. But if you're given two functions and you want to test to see if they're inverses of one another, that's easy to do by composition. Okay, so if you can compose one function with the other and you end up with just x as the composition, the identity function. X is called the identity function. So if you end up with the identity function when you compose the two functions, then you know that one of the functions is the inverse of the other. Okay. You can say that in either way. You can say G is F inverse, or you can say F is G inverse. All right. That relationship is symmetrical. So look at these two functions here. And one way to check if they're inverses of one another is just to figure out what the formula for the inverses are. Okay, that would take you a few minutes, all right, but it's not impossible. Or you can just apply that test. Okay, all right. So here's what I'm going to have you all do. I want you to apply the test, and while you are doing that, I'm going to actually take one of the functions and find the formula for the inverse using the system that I proposed a moment ago. Okay, so you do the inverse function property test, and I'll actually calculate the inverse of the function f. And we'll see who figures out if they're inverses of one another faster, right? See what I'm proposing to do, all right? So I want you to actually compose the two functions. So calculate f of g of x, or you can do it the other way. You can calculate g of f of x. And what are you supposed to come out with? X. So if you come up with X, then you know they're inverses of one another. What I'm going to do is I'm going to actually right over here, I'm going to write down the formula for F, and I'm going to flip the variables like I did a moment ago, and then solve for Y here and see what I come up with. If I come up with G, then I know that they're inverses of one another, right? Okay? All right, so y'all go and I'll go, and it's a race here. I'm done. I win. Did y'all finish? Okay. All right. Okay, so what did I do? Right? Remember what's the procedure if you're trying to find the formula for an inverse function? Just write y equal to your function formula. Invert the input and the output variable. So x is the input variable, y is the output variable, so I'm going to switch those, right? And now I'm going to solve for the output variable here, y. Okay? So what I do, I multiplied both sides of the equation by y minus 1. So that's easy. I get x times y minus 1 is equal to 2y plus 3. That cleared the fraction. Now I'm going to distribute this x. So I get xy minus x is equal to 2y plus 3. The reason I distributed the x is because I want to get all the y terms on one side of the equation and then all the remaining terms on the other side of the equation. So I move things around a little bit here. I move this x to the right and I move this 2y to the left. Okay? So notice the y terms are all here by themselves, and then I have the other terms on the other side of the equation, right? Now I'm going to factor out the y. So I factor the y out of these two terms. So I have y times x minus 2 is equal to x plus 3, and then I'll just divide both sides by x minus 2, so I'll isolate the y. So I get y is x plus 3 over x minus 2. Is that the formula for g? Yay! See, it is, right? Okay, so I know that those two functions are inverses of one another. All right. Well, that took me a few steps. See if you can. How did y'all do in composing now and get x? Anyone get to x? Did y'all get that finished? No? Okay. That was that slow? Is that hard? Maybe it is. Okay. This may involve some complex fractions, right? Okay. All right. So I want y'all to finish that. See if you can finish that. Okay. Well, maybe I won't have you finish it. All right. Maybe we'll get. Let's pick on Ignacio here. All right. And maybe we'll have Ignacio work up here. All right. That's okay, Ignacio. We're just gonna don't worry about getting. We're gonna finish it on the board, so they're gonna help you when you get stuck. All right. Okay. That's fine. Okay. So you can actually compose them in either order. Either order will work. Yeah, if either way it cancels and gives you x, then you know they're inverses of one another. Okay. What did you do? No. Mm-mm. Yeah, no, I don't know what you're doing. Yeah. I want you just to take this composition, right? I just want you to. Uh, oh no, don't. Yeah, no, not that part. No, you're doing the easy part. Okay. Well, it's supposed to be the easy part, but I think it ends up being kind of hard. All right. Yeah, that's right. That's what he's going to do. He's just rewriting the problem here. Or g of f of x, whichever one you think is strategic. Okay. Right, yeah, so there's the composition. So you have, yeah. All right. So now we end up with. So this is where you're gonna get. This is where people get hung up here, because now you have a complex. This is called a complex fraction, because you have a fraction inside of another fraction, right? Okay. And so that's always a mess, right? So usually your very first goal with a complex fraction is to make it uncomplex. You want to get the smaller fractions out of the bigger fraction. There's a couple of ways you can proceed to do that, okay, in algebra. Usually the shortcut method that's given is to multiply every term in the top and bottom by the least common denominator of your fractions. Okay, that's kind of the shortcut method. There's a longer method that's maybe a little bit easier to understand how it works, but it takes more steps. Okay, so let's go with the shortcut method here, Ignacio. So what would be the least common denominator of all of these terms inside your bigger fraction? X minus 2. Yeah, it's x minus 2. No. Yeah, no. Right. Yeah. Don't distribute. That's just going to be extra work. So multiply everything, but you have to multiply everything by x minus 2.
So if I multiply everything by x minus 2.
Yeah, so
2 times x plus 3 and then plus 3 times x minus 2.
Right. Yeah, so he multiplied the top. He multiplied the top by x minus 2, and here they canceled, right? And here, but here it didn't cancel, so you have 3 times x minus 2, right? Okay, yeah. Now do that in the bottom.
And now at the bottom it should just be x plus 3 minus x minus 2.
Perfect, right. See? And magically what has happened?
It's a lot easier.
Yeah. The complex fraction is no longer complex, you see. Now, you might say, that's a complex fraction. That's really complicated. Yeah, it's complicated, but it's not complex, all right? Because you don't have smaller fractions inside the bigger fraction. All right, so did y'all see that trick? When you're dealing with a complex fraction, all right, multiply every term, but you got to multiply every term in the fraction by the common denominator, okay? And if it's not a difficult common denominator, then things will dissolve nicely, and you'll end up with maybe still an ugly fraction, but it's not a complex fraction anymore. Now we're going to just simplify it. Mm-hmm.
Just for space. And now I'm just going to distribute the 2 and distribute the 3. And I could distribute the negative as well right here.
Right.
so I should just get 2x plus 6 plus 3x minus 6, all of that over x plus 3 minus x plus 2. And right here, these x's that cancel out. This is just going to reduce down to just 5 at the bottom.
5 at the bottom.
And right here, I have these 6's that cancel. And then I'm going to have a 5x, which just reduces down to.
Yeah, God, thank God, right? If that didn't come out in x, that would have been horrible, right? Okay, so there it is. Yeah, that just simplifies to x, right? And so, yay, yeah, you know that those are inverses of one another. Okay, well, you know. Maybe in some instances it's easier to find what the inverse formula is, right? And verify that two functions are inverses of one another. But sometimes that's not going to be easy. So sometimes the composition, composing the two, and then showing that the composition is x, that might be the easier way to go if you're trying to verify that two functions are inverses of one another. But usually in practice, you don't have to do that, okay, right? That's more of a theoretical exercise than it is practical. All right, now, let's also talk about graphs of inverses. We just spent a couple examples of finding formulas of inverses, okay? Finding formulas of inverses, but what do the graphs look like, all right? So if you have a graph of a function, what does the graph of the inverse look like? Okay. All right. So, but here's where again that you got to remember how inverses are defined, right? With an inverse, what do? You reverse what? The x and the y, the input and the output. So that gives you an important clue as to what the graph is going to look like. Okay. So suppose we have this. Function. All right. That I've got graphed here. That does appear to be one-to-one, right? Because you're not going to have a case here where, at least that we can see in this graphing window, you're not going to have a case where two inputs, two x values will give you the same y value, right? Okay. If you draw that horizontal line right across the curve, it's not going to slice it in more than one place, right? Okay. So apparently that does have an inverse. So let's see if we can figure out what the graph of the inverse looks like. Well, again, just remember what the inverse does is it flips the x and the y values, okay? So since we've got some ordered pairs that are identified on this curve f, let's flip those x and the y values, and then we'll know what ordered pairs are going to be on the graph of f inverse, okay? So let's see. We have minus 6, 0, right? Okay? Minus 6, 0. Let me erase this one because this is just a variable point. All right, so we have minus 6 and 0, right? So if I flip those two coordinates, right, if I flip the x and the y values, that gives me what? 0 and minus 6, right? So that's a point that's going to be on the inverse. 1, 2, 3, 4, 5, 6. There is 0 and minus 6, right? Okay, so that's on the inverse. 0 and minus 6. So I have minus 2 and 3, so what point's on the inverse? 3 and minus 2 right here, okay? And then I have 2 and 4, so I know what? 4 and 2 is going to be on the inverse right there. And I have what else here? 4 and 6, so I know 6 and 4. I think this is 6 and 4 right there, right? Is going to be on the graph of the inverse, okay? And now, if you can, try to connect those dots with a smooth curve, okay? Try to connect those dots with a smooth curve. And what you're going to get, if you plotted some more dots, is you're going to get a picture like this. There's the graph of f inverse, okay? Let me point out what's happened here, and you can actually prove this. The graph of f inverse, when we flipped all those points, what happened was we just rotated the curve around, and you can prove this. We just rotated a curve around this 45-degree line, y equals x. There's the line y equals x. And so what I did here, when I flipped all those coordinates, that just had the effect of rotating this curve around that line y equals x. Okay, so the inverse is the mirror image of the original. The graph of the inverse is the mirror image of the original graph rotated around the line y equals x. Okay, that's what graphs of inverses look like. Let me make sure I graph y equals x correctly. So that gives us a nice clue. For instance, if we wanted to write down the or draw the inverse of this function, square root of x minus 2. Okay. All right. First, let's see if we can figure out the formula for. Let's see if we can figure out the formula for f inverse. All right. Y'all think y'all can figure out the formula for f inverse? Let's see, how do we do that? Yeah, you flip and solve for x. So write this as square root of x minus 2, okay, and then reverse the variables, right? So you get x is square root of y minus 2, and now solve this equation for y if you can. So how would you solve this equation for y? Square everything. So you have x squared is equal to y minus 2. And then what? Add 2 to both sides. So y is equal to x squared plus 2, right? Okay. So there's the formula for the inverse, with a few little catches there that we'll talk about in just a second. That's almost the formula for the inverse, but I have to put a little bit of restrictions on this formula. But what's the graph going to look like? Even if you hadn't written down the formula, you could figure out, I think, what the graph is going to look like, right? Okay, let's draw it down here. Oh, we already found the formula, all right? So let's sketch the graph, all right? So how does the graph look like now? What does the inverse look like? You take it and you rotate the curve around what? Around y equals x. So y equals x is this 45-degree line, right? Okay, is this 45-degree line. So there's y equals x. So just take your graph and rotate it around y equals x. So when you take this curve and rotate it around y equals x, notice that's going to move it up here above y equals x, right? Okay, and let's see, what's the shape of that curve going to look like? I think it's going to be opening upward, right? Okay, let's move a few points. So here's the point that looks like 2, 0, right? There's the point 2, 0. So that's going to move up to what? The point 0, 2, right? Okay. Here's another point I can identify. That looks like what? 1, 2, 3, 4. Maybe up here. I don't think I plotted this very well. Right there, maybe? Okay. Did I do that right? I went a little bit too far, didn't I? Maybe right there. Okay, so there's another point that looks like it's going to be on the inverse, and then just there's your curve, right? So the graph of the inverse is going to look something like that. Now, when you graph x squared plus 2, right, which is supposed to be the formula for the inverse, when you graph x squared plus 2, you don't get just that. What else do you get? Yeah, you get the left-hand side of this parabola as well, right? So you would also get this piece over here. So this formula is a little bit misleading, right? Okay, that's not quite the formula for the inverse. Okay, somehow we have to get rid of this piece, right? Okay, so that's right. So you have to somehow monkey with the domain here to get rid of this piece. Let's see, how would you get rid of this piece? You have to have x what? greater than or equal to 0, right? So you would have to restrict the domain to x being greater than or equal to 0. Now, why is that justified to do that? Okay. Well, look at the original graph. Okay. Look at the original function here, f. Okay. Where does y start at? Y starts at 0, right? Okay. So you know in the original function, you know y always is greater than or equal to 0, and x also, you know something, is what? Greater than or equal to what? 2, right? So when you flip x and y in your inverse function, these restrictions are also going to flip. So in your inverse function, x is going to be what? Bigger than or equal to 0, and y is going to be bigger than or equal to what? 2, right? Okay. So that's why this left-hand piece you can leave off, because x has to be bigger than or equal to 0. Okay. And is y bigger than or equal to 2 here? I think it is, right? Okay, because that curve starts down here at 2. Okay. All right. We do have this, and so this is available on the homework. We do have a nice, let me see if I can show it to you here. We have a nice screen that you have access to, a link to on your homework assignment, which will actually allow you to graph inverses really quickly. So you don't have to try to graph a function and rotate it around a 45-degree line. Desmos will do that for you. Where do y'all see that? There should be a screen that's, there it is, graphing the inverse, okay? So all you have to do is type in a formula, and it'll graph the inverse for you. It's pretty good at doing this, so let's see, what was our formula? Square root of what? Square root of x minus 2, so there's the square root. So I want square root of x minus 2, right? And that's going to be the blue graph, okay? So the blue graph is going to be square root of x minus 2. And then there is the inverse. So the green graph is the inverse. So we did that pretty good, right, by hand. And, of course, there's the line y equals x, just to show you that the blue graph is rotated around y equals x to give you the inverse graph, okay? And then if you want to see points on the graph, just move this point around and it will move that point and show you what, of course, the corresponding point on the inverse is just going to be the coordinates flipped, right? Okay. So if you got problems in your homework, it says, what does the graph of the inverse look like? You can do that really. There's a link to this screen and your instructions for your homework, so you can graph it really quickly and not have to do that by hand. Okay. Some of those graphs may be complex to do by hand. All right, so I'm going to give you all another little practice here. All right. So we've seen a couple of examples of this. So I want you to do this, though, on your own. See, there's a function, x plus 4 over 3 minus x. I claim that has an inverse. Oh, let's graph it, and let's see. Let's convince ourselves of that. X minus 4 over, now that I bring it up, I didn't graph that. So let's try graphing that and see if we think it does have an inverse. X minus 4 over, I forgot what it was. X, what? X plus 4 over 3 minus x. All right, so let's put that in Desmos, if I can get back there. X minus 4 over 3 minus x. X plus 4. So x plus 4 over, no, that's not right. X plus 4 over 3 minus x. Okay, let's try it again. X plus 4 over 3 minus x. Ah. All right. Wow, you really have to look closely at this one, okay? Because it's got some branches to it, right? There's the original graph, okay? There's the original graph, has these two pieces, okay? Has these two pieces, this branch and this branch, all right? And so when you rotate that around y equals x, you get similar branches, but they're kind of reversed. So the green is the inverse function there, okay? So kind of a funky looking graph because this graph has some asymptotes in it, right? Its domain is not all real numbers, and that's the same thing for the inverse, okay? So there's what the graphs look like, but fortunately we're not trying to make the graphs, okay? All we want to do in this problem is just figure out what does the formula look like. So see if y'all can find for me the formula for the inverse function, okay? So everyone work on that. So what's the first step? Well, you can see the graph, but the graph won't help you, okay? The graph is really ugly. So we want the formula, though, okay? It's not really ugly. It's just got two pieces to it, so it's kind of a complex graph. What's the first step of finding the formula? Changing x and y, right, okay? So write it as y equals instead of f of x equals, and then interchange x and y, and then you've got to solve that new equation for y, okay? Y'all have that written down? You want me to write down, show you that last example that I did of this? Follow this as an example. Except you'll have x plus 4 over 3 minus x there. I'm going to need a brave volunteer too, so Okay, I'm going to ask Manny, did you finish it? Will you show it to us? Okay. You can write on this side. Find one of those that works. All right, so Manny's going to show us. Let me see if I can write it down while he's talking. I've got room here. Right. And then you switch your x and your y's. Switch the x and the y's, right? X equal to y plus 4 over 3 minus y. Over 3 minus y. So then multiply this by 3 minus y. Multiply this by 3 minus y. So then you get x minus 3 minus y is equal to y plus 4. All right, so multiply both sides by 3 minus y, so you can cancel the 3 minus y on the right, right? Yeah. Oh, all right. Oh, slow down. I did it wrong. 3x minus xy is equal to y plus 4, right? Mm-hmm. All right, so you're rearranging terms because you want all the y terms on one side, right? And then what? And then you rewrite this as y times negative x minus 1 is equal to negative 3x plus 4. Perfect. And then you just divide both sides by x, or negative x minus 1. Ah. So then you get y is equal to negative 3x plus 4 over negative x minus 1. Ah, and there it is, right? Nice, okay. So there's your formula for the inverse function. It just ends up being minus 3x plus 4 divided by minus x minus 1. All right, now let's finally at the end here, we got just enough time. Let me show you now a little bit of calculus, okay? All right, so because we haven't done any, all this has just been algebra, so we haven't done any calculus, but there is a relationship between the derivative of a function and its inverse function. And so here is actually the relationship. You have to kind of read this off in words a little bit to understand it, all right? So suppose you have a function and it has a derivative on some interval, and it's a one-to-one function. That means that it has an inverse, right? Then the inverse also has a derivative, okay? The inverse also has a derivative, and here's the formula for the derivative of the inverse, all right? So f inverse prime, read that carefully. That's the inverse function, right? So this is the derivative of the inverse function. Here's the formula for the derivative of the inverse function. So it's the derivative of the original function evaluated at the inverse, okay? So you plug the inverse function right into the derivative of the original function, but notice it's the reciprocal of this, all right? Okay, so look at that formula again carefully. If you want to know what the derivative of the inverse is, it's 1 over the derivative of the original function, but you have to plug in, you have to compose that with the inverse function's formula. All right? Let's try that. Okay? All right, so let's try that. So I'm not actually going to find the formula for the inverse, but let's try to evaluate that at some particular number. All right? Okay. So let's see. Suppose we've got this function. So f of x is 1/4 x cubed plus x minus 1. Okay? So there is the original function, 1/4 x cubed plus x minus 1. All right? And so my ultimate goal here is to figure out what is the derivative of the inverse at 3. Okay? What's the derivative of the inverse at 3? All right? So what's the slope of the tangent line of the inverse at 3? Okay? Now, if I just wrote down f prime of 3, of course, that would be easy, right? Okay? Because that is the derivative of the original function evaluated at 3, right? But I want to figure out what is the derivative of the inverse function evaluated at 3. Okay, so what did that? Let's remind ourselves of what that. Formula says. It says, all right. So if you want to evaluate the derivative of the inverse, right, at an input, what do? You take 1 over, right? You take 1 over what? F prime of. So you take 1 over the inverse of the original function, but where do you evaluate that at? What does that say? The inverse, right, okay. So this would be f inverse of, in this case, I want 3, right? So that's how I would figure out what the derivative of the inverse is at 3. It would be 1 over the derivative of the original function evaluated at the inverse of 3. So I have to figure out what is f inverse of 3 first. So that's why that part A came first. To figure out what the derivative is, I first got to figure out what is f inverse of 3. How am I going to figure out what f inverse of 3 is? Y'all have any ideas there?
3 equals 1/4 x cubed plus x minus 1 solve for x.
That would be one way. Okay, all right. So what Aaron is suggesting here is, look, you know, how does f inverse work, right? It switches inputs and outputs, correct? Okay, so you know that if you want 3 to be the output from the original function, and you want to figure out what the input is that gives you that output, okay? So what Aaron suggested is take 3, plug it into the output for the original function. In other words, make that the y, right? And see if you can figure out what the x value is that gives you that, right? If you can figure out what x value will give you an output of 3, then that's going to be the value for f inverse of 3. Oh, wow. Okay. So that looks nasty, though. That means I'm going to have to solve this equation. Wow, that's not an easy equation to solve, right? That's a cubic equation, okay? So that's not trivial to solve. But if we just have to solve it, I'm not sure if I can solve it algebraically, but I might be able to solve it by... Just what now?
Like if you plug in 3 in just the original equation and find what the output is, and then put the output in.
No, that won't help you there. Okay. So to solve this equation, Shelby, but you might try solving it by just doing a little trial and error. Okay. So see if you can just guess at the x that will give you an output of 3. Okay. All right. You might try doing some trial and error. That's one way of going about it. Okay. So just try some x values there and see if you can get an output of 3. Is 0 going to work? No. Okay. 1 going to work? No. 1 comes kind of close, though. All right. Is 2 going to work? What happens when you plug 2 in there? What works? 2 works. Yeah, 2 works, doesn't it? Okay. Yeah, okay. If you plug 2 in for x, you will get 3 for the output, right, okay? So there we got lucky, right? We just solved that by just trial and error. We figured out, okay? So we know then that F inverse of 3 is 2, all right? So what we just figured out here was F of 2 is equal to 3. So we know that F inverse of 3 is equal to 2, okay? Well, that was just really luck, all right, okay? That was just really luck. You also could have made a graph of F. So you can make a graph of 1/4 x cubed plus x minus 3 and also look at the graph and see if you can figure out what input gives you an output of 3, okay, by looking at the graph. So that might give you another hint of how to determine that. Well, anyway, we got lucky there. We know that F of 2 is equal to 3, so F inverse of 3 is equal to 2. All right, so let's hurry here. So what else do I have to know here to figure out what the derivative is, what the derivative of the inverse is at 3? So I know what this is now. That's nice. I know that's 2, okay? So I can plug that in. See, I know that all of this now is just 2, right? Okay, so what else do I need to know? The derivative, okay? The derivative of the original function. This is the derivative of the original function, right? Well, let's see if we can write that down really fast. What is the derivative of this function? It's 3/4 x squared plus 1, right? Okay, so all you have to do is plug 2 in here, okay, into 3/4 x squared plus 1. What does that give you when you plug 2 in there? Is it 4? I think it is, right, okay? So there we have it, okay? We know the inverse evaluated at 3. The derivative of the inverse evaluated at 3 is 1/4, okay? All right, well, there's one example, okay? I think we need to look at least one more example, right, before we try to use that in our homework, okay? But we've run out of time for today, all right? So, well, I think you got enough, though, to work on that extra credit if you want to, okay? But before you do that, the extra credit 5.3 homework, but before you do that, make sure you finish 5.2, okay? Make sure you finish the 5.2 homework, okay? And I'll see you on Thursday. We'll look at a couple more examples of this.